Hey everybody, so we're going to start off with some review board questions from the last lesson. Okay, so feel free to pause the video and try it yourself. The four vectors in the diagram represent forces of equal magnitude acting on the ball. Which of the following vectors best represents the net force acting on the ball? So let's give this a go. So I'm going to switch to my camera. So the first thing that we have to do is do a tip-tail vector addition. So I'm just going to do them A, B, C, D. So this is A. This is B. Make them the same size because they are equal magnitude. This is C. And then D goes up like this. And because it's at an angle, it's not going to make it all the way up to the top. So if we want to find the net force acting on this, then we just go from start to finish. And this is my F net. So it's down and to the left. So I would pick the answer that is down and to the left, which is A. Next one, a particular pass pattern requires a football receiver to run 15 meters north and then 10 meters, 35 degrees west of north. Calculate the magnitude of the resultant displacement. So for this one, what we want to do, so you could draw tip to tail, but it's not really going to help you. So this is 15 meters north and then 35 degrees west of north. So I'm not going north, I'm going 35 degrees west of north like that. And it's 10 meters, so it'd be like that. So when we draw our tip to tail, we don't get a right angle triangle, which means that we're going to have to do an RCS chart. This is X, this is Y. So the first vector is 15 meters and it goes straight north. Remember that we go 0, 90, 180, 270. So this is going to be 90 degrees in RCS. And then the other one is 10 meters and it's 35 degrees west of north. So it's going to be 90 plus 35, which will give us 125 degrees. So we go 15 cos 90, 10 cos 125, 15 sine 90, 10 sine 125, and we add up our two x's, so 15 cos 90 plus 10 cos 125, and we get negative 5.73, that's meters. And then second enter, switch all my coses to sines. Again, make sure you're in degree mode. And we get 23.19 meters. So now we're ready to draw our new triangle. So up and to the right is positive, down to the left is negative. So my x is going to be to the left. And it's going to be 5.73. Oops, let's draw that on the bottom, 5.73. And then my y is up, so it's positive and it's bigger, 23.19. Start to finish is going to be my resultant displacement. And it's just asking for magnitude, so I just have to go 23.19 meters squared plus 5.73 meters squared, all square rooted. Get rid of my negative sign in there. Don't put negatives, that just gives us direction. And square root our answer. We should get 23.9, which means that our answer would be 24 to 266. So our answer is going to be B. Cool. Okay. Well,
let's review Max's plan for the big ball.
So, projectile motion, I'll show a video of me using projectile motion in my wipeout video. Enjoy.
Safely on. Now let's review Max's plan for the big balls.
The x component, you're going at a constant velocity, so you use your v equals distance over time formula.
Oh, yeah.
Oh, right.
Right,
Yeah,
so if
of
you
course.
multiply by,
Yeah,
right.
it's simple science.
Yeah,
That's
when
all
you lay
I
it
get.
out like that.
Yeah, right. I think the big balls rejected his theory there, but here's one that works. Momentum plus big balls plus severe lack of coordination equals wipeout.
That checks out.
So here's a question for you. So a bullet is dropped and a bullet is fired perfectly horizontally. They're dropped and fired horizontally at the same time. Which one will hit the ground first? So think about it, think of your answer, then watch this video. Here's a Mythbusters video that shows them doing this actual experiment. Projectile motion. And let's explain why that happened in the Mythbusters video. So what we're going to do is we're going to draw a free body diagram and a vector diagram for the bullet that's being dropped. Okay, so what that's going to look like. So we're going to draw 3 different positions immediately when it leaves the hand, again when it's halfway, and then the bullet right before it's about to hit the ground. So a free body diagram would actually, I'm just going to give myself a little bit more space. Halfway, and then right before it hits the ground. So free body diagram is in free fall, right? So my force of gravity is the only force that acts on it. So we have that, and we'll ignore air resistance with this. So that is not a part of it. And then if we do a vector diagram, like we've done before, so initially it has no speed, but it's in free fall. So my acceleration is the same. My acceleration is always 9.81 meters per second squared in this. So initially it has no speed, and then it's going faster, and then it's going faster. So if we do the same thing and we draw a free body diagram for the bullet that's fired horizontally after it's left the gun, well, we can do that as well. So here, it's left the gun, it's almost hit the ground, and here's right before it hits the ground. So in terms of free body diagram, after it's left the gun, there's no more force applied acting on it. We'll ignore air resistance. So the only force that's acting on it is gravity. Right? So you can see the free body diagrams for both the same. And if we draw a vector diagram, what we find is that, well, the only acceleration that's acting on it is downwards because my net force is down, so my acceleration is down. So my acceleration is 9.81, so that looks exactly the same. The only thing that's different is because the bullet is fired, it's given a horizontal velocity, so it has a velocity this way, and because there's no forces acting in that x component, that velocity is just going to be the same the entire time. But in the y, it goes faster, and then it goes faster like that. So the vector diagrams look exactly the same in the y. The only difference is in the x. It has a little bit of speed. Well, a lot of speed if it's a gun and it's firing a bullet. So being dropped in the y looks exactly the same. So the bullet that's dropped and the bullet that's fired, they hit the ground at the same time because the y is the same. The only difference between the two is the bullet goes farther in the x. So 2 different physics principles are being used for the x and the y of the bullet that's being fired, the projectile. When friction is ignored, the x component moves at a constant speed, and we use physics principle 0, v equals d over t. When friction is ignored in the y component, it accelerates the same as an object being dropped. And when something's accelerating, we use physics principle 1, so VI, VF, DAT. And the only thing that's common between the x and the y is time. It's kind of like those navigation problems where time is the same in everything. Time must be the same because there's only one projectile, so we can't have it in different places at the same time. So time has to be the same in both the x and the y. We're going to jump right into a problem. So there's two types of problems that we're going to do. We're going to do horizontal projectiles, and then we'll do projectiles at an angle. So a cannon is fired horizontally from the top of a 10-meter tall hill with a muzzle velocity of 200 meters per second. And muzzle velocity just means the speed that it leaves the cannon at. What is the horizontal distance the cannon travels? Okay. So let's switch screens here. So I have my hill, I have my cannon, and my ball. My cannonball is going to follow a path that's like that. So we have our distance in the y, and we have the distance in the x. So those are two important things. So when doing projectile motion problems, we want to have our stuff organized, so we have an x and we have a y. So in the x, it's just moving at a constant speed the entire time, right? And in the y, it's just falling. And when we put those two motions together, the moving at a constant speed while falling, we end up with this type of arc that we call a parabola. So in the x, we're using physics principle 0. So we're using v equals d over t. And in the y, we're using physics principle 1, which is VI, VF, DAT. So we're going to say x for both of these, and we're going to say y for these, and we're going to fill in what we know. So I don't put anything with time because time is going to be the common ground between the two. So the question tells me that the hill is 10 meters tall, so this dy is 10 meters. And we're trying to find our dx. We want to know how far away it travels the horizontal distance. So initially, it's fired at 200 meters per second. So all of my speed is in the x. So this is going to be 200 meters per second. And like the Mythbusters video, dropping it is no different. My velocity is 0 meters per second in the y because it doesn't have any y component down there. Okay. And I also know that my acceleration is 9.81 meters per second squared. And I don't have to worry about negatives because everything's moving down. So I'm just going to say down is positive, so my acceleration is positive, and my distance that I move in my y is positive as well. Okay. All I need is 3 of 5, and I can find time, and time is the same between these. So time is the common ground. So I can use my formula d equals vit plus 1/2 at squared, and my initial velocity is 0, so it ends up being d equals 1/2 at squared. So I want to find time, so I move my 2 up top, my 8 down below, and square root it to find my time. So 2 times my distance, which is 10 meters, divided by my acceleration, all square rooted, will give me my time. So 2 times 10 divided by 9.81 square rooted. My time is equal to 1.4278 seconds, and I don't want to round it at all. So this is the same thing. And here I just use v equals d over t because it's moving at a constant speed in the x. And I can find my distance. So I type in that 1.4278 seconds, and I multiply it by my speed in the x, which is 200 meters per second. So I just multiply my last answer by 200, and I end up getting that it goes 285 meters. Okay. So there's a second part to this question. So the second part of the question is asking, well, what is the velocity as it strikes the ground? So right before it hits the ground, it's going to have this Vx, which is 200 meters per second, and it's speeding up, speeding up, speeding up, speeding up, speeding up. So it's going to have this Vy that we don't know, right? And I don't want to draw it like that. I want to draw it tip to tail. So I'm going to move it over there. And this is my true velocity of both of those added together in the end. So what I'm going to do is I'm going to erase this here. And I need to find my velocity in the y, because that's the other part of this. So I need a formula without time. So I'm going to use Vf squared equals Vi squared plus 2AD. And my initial velocity is 0. So if I want to find my final velocity, I just square root both sides, and I'll get that. So 2 times 9.81 times my distance of 10 meters, all square rooted, and I can find out what that final speed is just before it hits the ground. So 2 times 9.81 times 10, and I square root it, so I get 14.007. So this is 14.007. So if I want to find this, I just have to go 200 meters per second squared plus 14.007 squared, all square through root. I use my Pythagoras, so squared plus 200 squared, all square root, and I end up getting basically 200.5 meters per second. Okay, so it's going to be going a little bit faster, and I can also find this angle because it's asking me for velocity, so I just have to tan -1, opposite over adjacent, 14.007 divided by 200, and it's going to be a really tiny angle, so I tan -1, 14 over 200, and I get basically 4 degrees, and a good way of describing that is relative to the horizontal. So this is the horizontal, it's 4 degrees relative to that horizontal. So this is my final answer for that second part. Okay. So any questions, just let me know and I will help you out. So that's one type of question. The other type of question that we can do is projectiles at an angle. So we're going to draw a free body diagram and a vector diagram for an object fired at an angle. Okay, so we're going to do that on the whiteboard here. So projectile fired at an angle here. So when I fire something at an angle, that's my speed. Right, and we want to do a free body diagram. So for the free body diagram, right, all the different points here, it's still going to be the force of gravity acting on it if we ignore air resistance like that. So our free body diagram doesn't change, but what does change is our vector diagram. So that's my initial velocity, right? And what's going to happen is, so this is right as it's fired, and this is right before the end, like that. So with our horizontal projectile, all of our speed was in the x, but we see this speed is at an angle here. So this has an x component, and some of that speed is upwards, so it also has a y component. So it's got a really fast y speed, really fast x speed, right? And my acceleration is downwards, right? There's nothing acting in the x, so that means that Vx is going to stay the same. This arrow size is the same. But what makes these a little bit harder is that my Vy is going to be changing. My acceleration is down because my net force is down. My Vy is up. So when they're in opposite directions, it's going to slow down, slow down, slow down, slow down, stop. And here is its highest point. It's not going to have any Vy, right? And then, so my acceleration stays the same. My acceleration is 9.81 the entire time. And then as it starts moving downwards, right, it gets faster, faster, faster. So we're going to have a big Vy going downwards. Maybe I'll draw sort of a halfway point so that x stays the same, that x stays the same. My arrows don't look like that. So we're going to have a slower Vy here, and we're going to have stopped up here, and then Vy gets bigger. So really what we're doing is we're combining those horizontal projectiles that we did where it just goes up and down, and then we're combining it with a constant speed as we go across. And when we combine those two, we get this parabolic motion like that. So let's, oh, there's one more slide before we do a question. So there's some key points that we need to know. So the velocity of a projectile at an angle must be broken down into the x and y components because it has both. So to figure out Vy, so most of these angles are in RCS already, so all we have to do is we take our V, our initial velocity, and because it's y, we can use sine. Y sine, remember that one. And then for our x, we can use this. X is always cos, because our angles are in RCS, and I'll show you that when we do a question. So there's some key points that we need to know about this. So our maximum height is here. So this is our max height, and this is where our V and our Y is equal to 0. Distance traveled, so this would be our dx, our vx, or sorry, this is our Vy, and this is our Vx. And you can draw those tip to tail as well. If we just move it and we draw it over here, you can see that it's tip to tail like that. And you can see this angle here is already, whatever that angle is already in RCS because this is 0. So that's why we can always use sine and cos. Sine is y, x is cos. Okay, and then an important thing to know as well is because these, I always set up the questions so that they're nice and symmetrical. Whatever my Vy is over here, I'm going to have the exact equal and opposite Vy over here, but it's just moving down. So Vy at the start is equal to Vy at the end, but just in the opposite direction, and that's important when answering some of these questions. Okay, so let's do an example. A rock is thrown at an angle of 34 degrees relative to the horizontal at a velocity of 7.8 meters per second. Determine the rock's time in the air, horizontal distance traveled, and maximum height reached. Okay, let's draw a picture of this. It is 10:44 p.m. I am very tired from parenting all day, so yeah, let's get this done. Okay, so we can draw out a nice little picture of what's going on here. So we have a rock thrown at 7.8 meters per second at an angle of 34 degrees relative to the horizontal. So it's going to fly up like that. So the very first thing that we have to do is we have to break this speed into our x component and our y component. So to find Vy, we just take our speed, 7.8 meters per second, and y is sine of 34. Vx is going to be our 7.8 meters per second, and we have to cos of 34 degrees. 7.8 sine 34 is 4.3617, and our x component 7.8 cos of 34. It's going to be 6.4664 meters per second. And I'll use those whole numbers as I move through. I'll just write down the abbreviated version. So just like our last questions, we have to break it into x and y. In x, we're using physics principle 0 because it's going at a constant speed. In the y, we'll use physics principle 1 because it's accelerating. So we're going to use v equals d over t in the x. And these are vi, vf, dat in the y, except for time. And we'll fill in the stuff that we know. So the reason that we broke this up is because this is the speed in the x that's going to be moving the whole time. 6.4664 meters per second. And in the y, this is going to be changing, but this is my initial speed in the y. My acceleration is 9.81 meters per second squared because gravity is the only thing acting on it. And then the last one that we can fill in, if it's going up at 4.36 meters per second, right before it hits the ground, it's going to be going down at 4.36 meters per second. But because it's going down, we're going to make this negative. And because things are going up and down, we need to be careful with our positives and negatives. Initially, this is moving up, and then after, this is moving down at the same speed. And our acceleration is downward, so we want to put a negative. So again, the common ground between these is time, and that's what the first one is asking. So we want to find one without distance. So we're going to use acceleration equals final minus initial all over time. Move our time up top. Move our acceleration down below. My final speed is negative 4.3617 meters per second. And my initial speed is positive 4.3617 meters per second. All divided by negative 9.81 meters per second squared, and we should get a positive answer because time has to be positive. So negative my answer from before minus my answer from before divided by negative 9.81, and I get my time to be 0.88923 seconds. And I don't want to round that yet because I'm going to use that moving forward. So 0.88923 seconds. 0.88923 seconds. Okay. So now we can easily find our distance in a y. So we want to find our horizontal distance traveled. So let's do this one first. We can just use v equals d over t. And we want to find distance. So 0.88923 seconds times by the 6.4664, the velocity that we have there. And we get our horizontal distances 5.75 meters. Okay. The last question is asking our maximum height reached. And this is a little bit trickier because, well, we have to use different numbers. So we use this number here that is the very end, but I'm going to do a different VI, VF, DAT for our maximum height reached. So my initial velocity is going to be the same. It's still going to be that 4.36 meters per second upwards. My acceleration is still going to be 9.81 meters per second squared. But at this highest point in the y, my final velocity is 0. So I can use these three pieces of information to figure out my distance. So I want a formula without time. So I'm going to use VF squared equals VI squared plus 2AD. I'm going to subtract the VI squared from both sides. So I end up with VF squared minus VI squared equals 2AD. And I'm going to move my 2A underneath. Okay. So now I can fill in my numbers. 4.3617 meters per second squared minus 0 squared. Oops, sorry, I did that backwards. Let me try that again. So my final speed is 0, and I'll subtract 4.3617 meters per second squared divided by 2 times negative 9.81. So you can see this is nothing, but this negative and this negative will cancel out. So we'll get a positive distance, and it goes up, so we should get a positive distance. So all I have to do is 4.3617 squared, don't forget to square it, divided by 2 times 9.81, and I get my maximum height is 0.97 meters. Okay, that is projectile motion in a nutshell. So that's a tricky concept. So on Tuesday, we are going to do a lab. I still have to work that out, how it's going to do, but it's going to be an online lab where you get to practice these skills a little bit. And what you can also do is spend your long weekend working on these questions, and feel free to email me and I will answer any questions that you have while working on these. And I know you have all long weekend to work on it because no one's going to grandma's for Easter dinner. You're all stuck at home. So yeah, work on these questions, do them all. Email me if you have questions and we can figure it out. And this is our unit review because we're done the unit. So next week we're also going to test on these ideas. Again, I'm not sure how that'll work. I'll work out some of the kinks over the long weekend and next week and let you know how we're going to test on these ideas. So work on these, enjoy, and thank you for watching the video, and have a wonderful long weekend.